Good. Okay. Well, good morning, everyone. So my name is Fedor, and today with me is Thomas. Later on this afternoon, there will also be Ola, and Thomas and Ola will be demoing this afternoon session. So for those of you who will be following both of them, the afternoon will be demoed by Thomas and Ola, which will be more on periodic systems. So hopefully Thomas can have a look at the chat whilst I'm talking. As we just briefly talked about, the idea would be that we give a very short introduction to the Amsterdam Modeling Suite and then do a hands-on demonstration of a few of the functionalities which are available. And for that, it would be useful if you have already installed the Amsterdam Modeling Suite. So I think in the chat window, you can still find, I'm not sure if I can see the chat window now, but in the chat window, you should be able to find the main download page and the password and username. So let me drag our website here. On the support page, you can go to the download part, and there you will find the main binaries for Windows, Mac, and Linux. So with the username winter and the password virtual.cc, both starting with a capital, you should be able to both download the software and automatically get a license installed, so you can follow along with the hands-on part. All right, so if you have any questions, just drop them in the chat box. Hopefully then Thomas can look along with me. And if you have any license issues, just let us know and we'll see if we can sort you out. Good, okay, let me start with a quick introduction. Quick introduction to the Amsterdam Modeling Suite. So in the morning session, again, we will be demoing mostly molecules, and in the afternoon session, the focus will be on periodic systems, their electronic structure, their mechanical properties, and that will be demoed by Thomas and Ola. A little bit of background of where we come from. So the people who have been listening to the discussion session before, would have understood that we're based out of the Netherlands. We're based out of Amsterdam. And in Amsterdam, in the 70s, Professor Evert-Jan Barends was pursuing his PhD and essentially making pragmatic methods to understand and predict chemistry, so understand spectroscopic properties, reactivity, in particular for inorganic molecules. And he was borrowing the methods based on density functional theory, which at the time were very well respected in the physics community, but weren't liked at all in the chemistry community because it was considered not really ab initio. But it was the only pragmatic way that one could study these type of molecules, so transition metal complexes, by using computational techniques. And so they discretized the methods that were used in the physics community for looking at bulk structures, and as such it was possible to start understanding and predicting reactivity of, again, inorganic molecules with a particular application to catalysis. So by having pragmatic methods that would allow you to predict, let's say, better catalysts or get an understanding, there was huge interest, especially in the Netherlands here, from industry using these methods. And so in the 80s, there was support from these companies through so-called extramural contracts to help further develop the software and get actual hands-on training here at the Free University in Amsterdam, where we spun out actually 25 years ago. So last week we celebrated our 25th anniversary as a company. So in the years that followed, especially starting in the 90s, and Tom Ziegler, who joined the ADF development community relatively early on, was specifically pivotal in that for developing new methods and spreading the word that DFT was a pragmatic method to understand chemical problems and to be able to predict and understand chemical reactivity and properties through using these density functional based methods. And so especially in the 90s, there were a lot of papers that were putting forward new method development as well as pragmatic applications. And I think having that hand by hand, so method development and finding real life applications, that was what really made density functional theory grow. Especially in 1993, when Gaussian made the modified Becker-3-Lip potential or exchange correlation functional available, which was at that time a really efficient and pragmatic method also to study organic chemistry. It became more and more popular, and I would say nowadays it is a mainstream tool for theoreticians as well as experimentalists alike to help them in their chemistry research and development. Also in the material science, things have evolved a lot since the early days in the 60s and the 70s of the density functional theory, and it's becoming a more and more pragmatic tool also to develop better materials. Okay, so currently in Amsterdam we have around 25 people, and so most of them are scientific software developers, so they've found a place within the company to continue doing software development. And we do have a lot of collaborations going on worldwide with companies, government labs, and academic groups worldwide, which helps us to implement new functionality. And then on our side, our developers deal with all the boring stuff. So that's what we also talked about a little bit, right? Sustainable software. So as a postdoc or a PhD, you just need something that works. But how do you make sure that it is working on all sorts of platforms that will work 5 years down the line when the next PhD student comes along, and that is essentially what our software developers are good at, and so that is their day-to-day job as well as developing new functionality. All right, so just a whirlwind tour through these software tools that we have. So in the 70s, we had our molecular DFT code ADF, which is still the main code that people are using when we talk about the Amsterdam Modeling Suite. It is still the most powerful tool for dealing with spectroscopic and reactivity properties of inorganic molecules, but there are also wide-ranging applications to organic chemistry. In the 80s, especially also in the view of catalysis, there was a periodic density functional code developed. It is called BAND, and that is specifically suitable for dealing with periodic structures. And Thomas will introduce that in a little bit more detail, or actually give you hands-on examples on how to use that in the afternoon session. Then a little bit further down the line in history, we started working on faster electronic structure methods, and particularly we incorporated Jimmy Stewart's MOPAC, semi-empirical code, and we worked with a couple of groups to implement density functional based tight binding, which essentially is a quick way to get rather good approximate DFT results. And that can be applied to molecules as well as periodic systems. Fast forward a little bit to the 2010s, if you will. We started developing together with a Dutch person, Arie van Duin, reactive molecular dynamics, ReactFF. It's a reactive force field. It doesn't use electronic structure, but it's typically parameterized against DFT, and that allows you to study really large systems where you can also have bond breaking and bond formation, as opposed to force fields that have harmonic potentials. And so those are all our atomistic codes. We also have currently one code to do microkinetics, and more will be developed in the area of mesoscale and specifically in the context of reactivity. On the continuum end of the length and time scales, we have one module which I'll very briefly introduce. It's called COSMOS, and that allows you to deal with properties, thermodynamic properties in solution. Again, the underlying theory is based on DFT, so it sort of nicely fits in the whole Amsterdam Modeling Suite package as a whole. So you can run all of these codes through the graphical user interface. If you don't want to do that, that's also possible. But if you don't want to do that, then probably you want to zoom out of this tutorial because this is what we'll be using mostly for the remainder of this and the afternoon session. We also talked at length about Python and scripting in general. So myself, I grew up with Bash scripting, and there is still extensive support for using Bash scripting around the Amsterdam Modeling Suite. So allow you to, let's say, go through a list of coordinates and use them with a certain setup for your calculation or pass them on from one code to the next. However, more and more effort is going into Python-based tools, and if you're interested in learning more on how to do that, in the afternoon session we'll use a little bit Python scripting, and my colleagues Thomas and Ola are very well versed in using these Python tools. So if you're interested in learning more about that, I would suggest to definitely log into the afternoon session. Good. So all these modules on the left-hand side. So I mentioned those previously, from ADF to COSMOS. You can use them through the command line. You can use them through the graphical user interface and this Python scripting tool. There's also a centralized driver, which we call the EMS driver, which can be used as a very fast way of connecting all these different modules together with the Python tools. It's also a very generic driver that allows you to do complex potential energy surface tasks. So from simple geometry optimization to Monte Carlo. Again, the afternoon session we'll demo this when we look at insertion processes in batteries. And allows you also to connect to external code. So if you have any code that gives you energies and forces, you can plug that into the centralized driver, and that allows you to quickly use different sets of codes to do the same type of tasks that you could want to do on the potential energy surface. On the right-hand side, these are the typical applications that people would use as software for. So originally it was mostly spectroscopy and inorganic chemistry, but there are more and more applications where people use the Amsterdam Modeling Suite nowadays. All right, I'd like to get started with a little bit hands-on demo. So I would like to skip the introduction of all the other codes. The slides are available online as well. And so they give, let's say, one slide introduction on each one of these modules. So if you want to look into that, you can just download the slides from the news item on our website. So if you go to our website, you go to the homepage, there should be the news item on the hands-on online workshop of today. And there should be links there to the introduction slides, also the exercises. And there will be, there are zip files with all the inputs. So I realize sometimes I might go a little bit too quickly. So if we're setting up calculations and you can't follow along, if you download that zip file, you will find all the inputs of the calculations we will be running. And the same goes for the afternoon session. So the afternoon session will start with Thomas, who will have two hands-on examples of 2D electronic material and mechanical properties of a linear polymer. So maybe you want to download the input files just in case if something goes wrong in setting up your input file. After Thomas, there will be two examples by Ola, who will be shooting, I think, a buckyball at a carbonaceous surface, and who will be running a Monte Carlo simulation on lithium insertion into sulfur anodes. Good. Okay, so let me get out of this presentation and then see if we can get started with some hands-on exercises. So again, these slides are available for download. The idea is that we will first start build a simple molecule, propanol in this case, and we will do that in a couple of different ways so you can familiarize yourself with the graphical user interface, and then we will start running a couple of quick calculations on its spectroscopic properties. After that, I'd like to go to a little bit more complicated system. We'll be looking at a metallocene system and specifically a Ziegler-Natta catalyst, and look at its transition state for ethylene insertion, so for the insertion step of the polymerization. All right, so first thing to do is get the graphical user interface fired up, and if you have managed to install the binary, if you're on a Windows machine, there should be an ADF jobs icon. If you're on a Mac machine, then it should be in your application folders after you've installed it. And if you double click that ADF jobs, the first thing you will see is rather boring. And let me see, obviously that goes to the wrong screen. So apologize in advance. It will probably happen that all sorts of new input screens will end up on the wrong screen. I'll try and drag them into the screen that you can actually see. So this is the first thing that you will see when you fire up the graphical user interface. It is, as I mentioned, a simple job bookkeeping tool, and it will show you all the jobs that you have on your computer. You can switch here from all the files to a folder view if you are well organized and you put them in a proper folder structure. That could be sometimes a little bit easier. And each one of these jobs will have at the right-hand side some sort of job status. So a full circle means the job is finished. If we see a triangle, there was some warning, so you may want to look into that. If you see a sign like that, it means there was an error. So definitely you want to look into your output file and make sure that this error doesn't affect your calculation, or that you solve it and bring your calculation to a proper end. Each one of these jobs has associated with it a number of different files, and we get into that later on as we start going through a couple of these examples. So let's start with building new molecules, and we do that by choosing the SEM menu and selecting new input, and that probably will end up on my right-hand screen. Indeed, let me drag it over to a place where you can see it. All right, so this is the input window, and by default, it will take you to ADF, which is our oldest and still most often used code. And that is a molecular DFT code, so it will give you building tools for building molecules. So in the afternoon, you will learn a little bit more on how to build periodic structures and work with that. For this session, we'll mainly focus on molecules. So we had a couple of examples on doing spectroscopic properties of a molecule which is called acrolein or 1-propanol. Let me see, let me grab here on the side what I wanted to do. So there are various ways you can start building molecules. And so on slide 9, of the exercises, there is a link to a tutorial on building molecules. So if you're interested in learning different ways of doing that, then maybe in your own time you can have a look at that. In this case, we want to start building this little molecule here in a couple of different ways. So one option is to search for it in the graphical user interface. And the search functionality is this little magnifying glass here on the top right. So if we click on that, it gives us a search box and we can start typing propanol, see if we see something useful here. By default, it will give you first entries from the documentation part. So this is offline documentation that is shipped with the graphical user interface. After that, you will find molecules and maybe even periodic systems. So in this case, you will see an entry here, propanol or acrolein. So that is its common name, and it has in between brackets ADF. And whenever you see that, that is a molecule that has been optimized with certain settings in ADF, which have been used to parameterize this Cosmores, the thermodynamic code for properties in solution. And so if we select that, we get a pretty well optimized structure. So the specific settings in terms of the calculation, it has been used. So this calculation has been run with Becker-Perdue, exchange correlation functional, triple zeta basis set, scalar relativity, and normal numerical quality. So now we have this molecule, we can start running calculations with it, but let's delete it and find a couple of different ways of building these molecules. So we get a little bit feeling on how we do this. So I now shift and left click, select the molecule and delete it. So press delete or backspace, the molecule is gone. And let's see if we can build the molecule from scratch. And we'll use these tools here at the bottom. So if I press on this carbon atom, I can start drawing carbon atoms into the input window. By default, we'll get single bonds. If I press 2, I'll get a double bond. And now I want to have a single bond again. I press 1, I get a single bond. Now I want a double bond, and I want actually an oxygen atom. So I select oxygen here, and I create a double bond here. Now these single and double bonds are used for the graphical user interface to sort of guess what is a reasonable distance. Now I've got a pretty bare bone system, so I want to add hydrogen atoms. I will deselect any atom by just left clicking anywhere in the input window. And now I select the whole molecule by pressing Ctrl A, so select all the atoms in the input window. And I want to add hydrogen atoms, which can be done by pressing Ctrl E. So some of these shortcuts can be rather useful, and I borrowed this from Thomas. So in the hands-on slides, you will find a couple of these useful GUI manipulation tools and shortcuts. So they can be pretty useful. Okay, so now the system, as you can see, is not really flat as it should be. So we'd want to sort of snap this geometry into a place where it becomes flat and becomes a little bit more reasonable. And the tool to use in the graphical user interface is this little cogwheel here. So if you hover your mouse on top of that, it will give you a little bit more information. By default, it will use the universal force field to optimize your system quickly to the nearest local minimum. So if we left click on that, it will do a very quick geometry optimization. And as you can see, it's already flattened out. But if we want to make sure it is proper mirror symmetric, we can use another tool here. This is the symmetrize button, this little star button. If we click on that, it will ensure that we get the CS symmetry. We want to do geometry optimization or quick cleaning up of this molecule with MOPAC and DFTB. That's also possible. We can right click on this cogwheel here and we can choose MOPAC, for instance, Jimmy Stewart's fast semi-empirical code. And that usually gives pretty reasonable geometries. It also has parameters for transition metals for most elements in the periodic table. And similarly, you can use density functional base tight binding for geometry optimization. The default method that is used is Grimm's extended tight binding, GFN-XDB, so that too can deal with transition metals as well. Good, so if we click on that, we left click on DFTB, indeed it will tell you that it will use GFN-XDB to pre-optimize your molecule, and if we wanted to change that, we can change the behavior of that DFTB pre-optimizer if we go to the DFTB panel, which we'll do in a second. All right, so both of these geometries should be pretty reasonable. Let me, in the meantime, see if there's any questions in the chat that we need to address.
Okay, so there's been a couple of questions about pricing and things, but Thomas has included a link to the SCM website where you can get quotes for that. And I think Rika's fixed her number of double bonds, but I think everything else, if anyone does have any questions, if you want to ask them very quickly now.
Yeah, so what I'll do actually, so now I see I'm learning as I go along as well. I put the group chat on the right, and indeed Thomas is reading along as well. So if you wanted to change, let's say, the bond order of these, and so bond orders don't mean anything to electronic structure codes, right? So in this case, just the guide to the eye, to the graphical user interface, they mean something for force field-based methods, but for any electronic structure method, they don't mean anything. If we wanted to change them, we could right-click on a bond. So if we select a bond and right click on that, we can change the bond order. So we could make it aromatic if we wanted to. As you see, it's made a little bit shorter. Or you can use this thing here. And there we can also change it back to single, for instance. So there are many different options that you could use to do this. Okay, so those are a few options that you can use to get started with drawing structures. What's another useful option maybe is to use smile strings or inky strings. So we're working with acrylin, and if we just type that into your favorite search engine, usually that will take you, for instance, to Wikipedia. If you go to Wikipedia, there you will find inky, as well as smile strings. And so the smile strings you can work out by yourself. Inky is a little bit human readable. You can use both. So let's see if this works. So just copy this. We go back to our graphical user interface. I will delete this molecule again. And now I just paste it. So Control V or Command V on your Mac. You'll see, smile strings just look at connectivity. And so they get that we have a carbon atom, an sp2 carbon atom connected to another sp2 carbon atom, to an sp2 carbon atom connected to an oxygen. So with a double bond, and that is what this smile string means here. So there's a single bond between these two carbon atoms, and it doesn't look so nice. So maybe, let's see, we can pre-optimize this. All right, so now it gets us in this SSys configuration, which gives me a chance to demonstrate another functionality of the graphical user interface. So we can select, so I select one atom, hold shift, select another atom, and another atom. And now we can use this slider here, or this input box, to change the dihedral angle, in this case to 360 to get the S-trans configuration. Maybe you want to pre-optimize it again and use the symmetry function to symmetrize it. All right, so smiles can be useful. Let's see if we can just copy the inky string here. So just copy that whole bit, delete this molecule. So Control A, delete, edit, paste. And we see that is already a little bit more reasonable structure. So whatever the inky magic is, it gives at least a better starting point in this case. And I understood that inky will also be further extended to include transition metals and so on, which I guess will take a little bit more time also from the graphical user interface developers to support, but that could be a really nice way of quickly importing molecules. Now let's say you've got a molecule which is part of a crystal structure. Then in the afternoon session we'll import ZIF files, and if you have a periodic structure and then you change to ADF, it will automatically go to a molecular representation, so you can cut and paste molecules from your crystal structure as well. Good. Okay, so those are a few options to build new molecules. Now let's actually get started with running some calculations. And let's see if this is symmetric here, and just for the heck of it. Okay, so it is mirror symmetric. Now let's see if we can calculate the infrared spectrum. Let's get started with ADF. And so ADF is a DFT code. So for DFT code, we need to think about a couple of input options, particularly the exchange correlation functional. And so you'll find a drop down here. So it defaults to local density approximation, and we can choose from a number of different categories. In this case, we'll go with dispersion corrected DFT, and we'll choose PBE with the Grimme D4. So that's the latest set of dispersion corrections. And then in ADF, there are different ways of dealing with relativity. So ADF doesn't use pseudopotentials. You can freeze the inner electrons, but then you still get the proper density, you get all the electrons. So we don't have relativistic pseudopotentials either, but we have very good ways of including relativistic effects. And so by and large, what you would use most of the time is scalar relativistic approach, and in the context of ADF, that would default to zero order regular approximation, which has been developed by Erik van Lente, which is one of our oldest ADF developers. And that's a really efficient way, a good way to include relativistic effects for most intents and purposes. If you want to go to spectroscopic properties, and particularly spectroscopic properties of electrons which are sitting very close to nuclei, and even more so if those nuclei are getting heavier and heavier, then sometimes you'd want to include specific spin-orbit coupling effects, and so that can be done in ADF using a two-component approach, again using Zora or using X2C. Usually for geometries, spin-orbit coupling is not important unless you go to the very heavy elements. So let's say the 6p elements or the super heavies, and then you could also run geometry optimization using spin-orbit coupling. Now for a molecule like that, relativistic effects are going to be virtually non-existent, but it doesn't cost you anything to switch them on anyway. So I would suggest always to switch on scalar relativity unless you have a good reason to use something else. The next thing that we need to think about is a basis set, and we can discuss this maybe better, let's say, in the session in between the two demo sessions. For geometries, usually double zeta with polarization is a pretty good choice, and for a number of spectroscopic properties, that can also be a good starting point. And sometimes you want to go to a little bit larger basis sets. I mentioned we don't use pseudopotentials, but you can freeze the inner electrons. And the way that works in ADF is that whenever we calculate a molecule, the starting point are the fragments, and the fragments by default are the atoms, and those atoms are calculated with a fully relativistic calculation, and then we calculate the whole molecule as let's say a change in the electronic structure based on those atomic fragments. And so that atomic calculation used as a starting point can also be used to freeze the inner electrons. So if we think about a carbon atom in a bonding situation like that, the 1s electrons are probably going to be pretty similar to the atom, so the fully spherically symmetric atom, to the bonding situation in the sp2 situation it is in the acrolein molecule. So that can help you to speed up your calculation. And so frozen core approximation can be a good way to speed up your calculation, especially for geometries. Again, for spectroscopic properties where we have these electrons close to nuclei, you may think about using no core. And for certain sets of exchange correlation functionals, you would actually have to use all the electrons as well. In this case, it doesn't really cost you much to include all of those 1s electrons as well. Good, let's just keep all the other settings as they are. There's one more setting that you have to deal with in density functional theory, and that has to do with the density integration and the density fitting that we use in ADF. Those can be handled by a single parameter, and normal usually is good enough. If you want to fine-tune all of that, you can click on one of these little arrows here. That will take you to the numerical quality window, so you can change the accuracy for the integration, the density fitting, and this particular resolution of the identity if we use hybrids where we include Hartree-Fock. On this panel here, you can also change and on this panel here, you can also change the specific settings for each one of these regions. So let me talk about that about it a little bit later on. So if you have a larger molecule, sometimes you want to have a little bit higher accuracy on part of your molecule, so you can change the specific quality settings for part of your molecule if you wanted to. And for that, you can change you have to divide your system into different regions, and that can be done in a model regions panel. All right, let's save this molecule and save the input. And we save this by default. It should take you to ADF data. Let's save this as infrared spectrum propanol, and that should update your ADF jobs. So now we have a job here which has an empty circle, which means the job hasn't been running yet. So we go to job run. By default, that runs in the sequential queue, and the sequential queue is the queue which is local to your machine. You can change that behavior if you wanted to, and that can be done here in the queue menu from ADF jobs. So I could edit the sequential queue. You can also change the default queue. Let's say you're always running calculations remotely. That can be done as well. So you can define different remote queues, and then you can set that queue as your specific your specific default queue where you want to run your calculations. Okay, so I got a question from Thomas, which he got privately, and so I guess I didn't explain this yet. The basis sets that we use in ADF are Slater type orbitals, so they have a exponential decay rather than a Gaussian decay. So any of these basis sets here, you will find for all the elements in the periodic tables, basis sets with different different accuracies. So as I mentioned, DZP double zeta with one polarization function is usually good enough for geometry. Sometimes you want to go to triple zeta. And for spectroscopic properties, yeah, you'd have to think about the type of spectroscopic properties. So for infrared, you know, if your geometry is good enough, then your infrared spectrum is also going to be of similar quality. If you want to go to NMR, maybe you want to increase your basis set quality a little bit as well. These Slater type orbitals, they have the benefit that they describe the nuclear cusp. So they have a finite gradient at the nucleus, and they have the right decay at long distances. So for a couple of properties, spectroscopic properties like NMR, but also UV vis, X-ray, those orbitals describe a little bit better because they're closer to the proper solution for hydrogenic atoms. They have a little bit better description of especially the short and the long range regions. So if you're familiar with Gaussian type orbitals, then there's no direct translation, but if you use something that has double zeta quality, or if you use a Popel basis set, split valence basis set, 631G star or whatever, so something of similar quality to DZP. Usually, because of the correct long-range decay behavior and the nuclear cusp, the Slater type orbitals tend to converge a little bit faster than Gaussian type orbitals. So if you're interested on that, I can send you some references that discuss that into a little bit more detail. Good. Okay, so hopefully your calculation will have finished. So I'm running quite a few things on this machine, so I get a warning here that there's some slow communication going on. That doesn't really affect the calculation itself, so I can now start look at the result of the calculation. I mentioned that each job has with it associated a few files. The log file is just a short summary of the calculation. The output file is the full-fledged output of the calculation. For those of you, if you're still around, that are more interested in running command line, you will find also a run file, which you can use for running through the command line. And it's just your input system, basis set settings, GUI bonds you don't need, it's just for the graphical user interface. And these are the density functional settings here. So the exchange correlation functional and the relativity settings. That's it. All right, so actually I just ran a geometry optimization, a single point calculation, because I didn't run the geometry optimization in the infrared. So sorry about that. We switch here from single point to geometry opt and frequencies. And so that's a specific option to ADF, which is a little bit separate from all the other programs at the moment, which have been, let's say, ported to the Amsterdam Modeling Suite driver, which makes it easier to switch from one computational engine to the other. So if we switch to DFTB, this will look a little bit different. Okay, so sorry about that. Let's save this file, and it will ask us to overwrite. We'll overwrite this, and let's run this again. It shouldn't take too long though. Let's have a look at the run file now. So if we double click that run file, here we'll find geometry. This is our geometry block. So just do a geometry optimization. And this means calculate the frequencies analytically if they're available. And this scan frequency means that if we have any imaginary frequencies, scan along those modes to ensure that it's indeed a imaginary frequency. Okay, let me close this window. The log file I mentioned is just a very short summary of your calculation. And let me drag it into the right input window. So for ADF, usually what you will find, the first part is just generating these atomic fragments that I mentioned are used as input for the molecular calculation. So it's not really interesting. And then finally, we get to our ADF program, where it tells you this is the symmetry of the system. These are your coordinates. And if you wanted to, you can copy and paste those into the graphical user interface as well. So if you have, let's say, a log file of a calculation, and you want to reuse one of those geometries, one quick way would be to copy and paste those, or we could copy and paste them from ADF Movie, which I'll show momentarily. Then we see also a little progress report here on the geometry optimization. So we want to get the gradients to below a certain threshold as well as have the energy converged to a certain threshold as well. And you can change those thresholds as well. So here, after a couple of steps, in my case, it's 5 steps, all of these criteria are met, the geometry is converged, and then we do one final calculation, recalculate the energy, and then it moves on to the frequency calculation. And since we have analytical gradients here, it will do an analytical calculation of the hessian and then calculate the normal modes in the infrared spectrum from that. So hopefully this has given you enough time to finish your calculation on your own machine. Once we have a new geometry, the graphical user interface asks you, do you want to read in the new coordinates? So let's say yes. And there's some slight change here in the geometry. And if we go back to ADF jobs here, if we switch from SCM to movie, we need to select the job first. Sorry, select this job. We go to SCM movie. That will, of course, on the wrong screen, give you, let's say, visual progress on how the geometry is optimized or how the geometry changes. And we can also plot in this ADF movie, for instance, how this distance changes. So if we select one atom, hold shift, select the other atom, we can graph the distance on the same plot. So we can see how that distance changes during the geometry optimization. And similarly, if we select 3 atoms, we can also graph the angle here. Right, so that is now plotted. Since we only have 2 axes which we can plot, it automatically generates a new graph here. Good, so let's say you have a geometry and you're monitoring this geometry optimization and it doesn't really work well, and you want to select one of these points here. You can also update this particular geometry into the GUI, as I mentioned a minute ago. So that's done here from File, Update Geometry and Input. It will then take that particular geometry and go to ADF Input and use that. So if you monitor your geometry optimization and it doesn't go that well, you can use that trick to update your geometry and then start from that. Good, since we've run infrared calculation or a frequency calculation, we get an infrared spectrum. So if we switch from SCM to spectra, sorry that it always pops up on the wrong screen, we get here an infrared spectrum, and you see here the symmetry of the modes, and they're ordered according to their frequency. You can select one of these modes and see what frequency it corresponds to. If you want to change the appearance of this spectrum, you can play around a little bit with the broadening. So you can choose either a Gaussian or a Lorentzian broadening, and you can change, for instance, the width and get a little bit narrower spectrum. So this is just a tweaking tool to make it a little bit more to your liking, so to say. Whilst we're here, let's see if we can also visualize. Sorry about that. I visualize the partial vibrational spectra, PV-DOS. So if we select one atom here, you can see to which one of these normal modes that atom contributes. So if we look at the CO, we see the frequencies that these atoms are contributing to. All right, so let's close this window and see if we can do a little bit quicker calculation, but now using density functional based tight binding. So we go back to our main input. We switch from ADF to DFTB, and I mentioned this looks a little bit different here. We want to do a geometry optimization and also calculate the frequencies. So the infrared spectrum, we can click here. Yes, we tick this button here, and let's save this as infrared spectrum propanol DFTB. And I'm using now this Grimm's extended tight binding. For organic molecules, you could also think about using a different set of DFTB approximations. So you could use DFTB3, third order density functional based tight binding, for which we have to choose parameters, and then I'd recommend 3OB, 3.1, which are pretty decent, especially in combination with Grimm's third generation of dispersion corrections with Becker-Johnson damping. Right, so this is one particular set of DFTB approximations. So the DFTB3 model together with these dispersion corrections and these parameters, they're pretty decent for a large range of organic molecules. And so if you would use that a lot of the time, you can also save that as a specific preset. You can quickly load those settings as well. All right, let me switch back to GFN-XDB and just run this calculation. So I click File, Run, because I already saved it as a different file. And let's see how long that takes. And so that shouldn't take more than a couple of seconds. All right, let's have a look now through the SCM menu directly at the infrared spectrum. And we can see we get a pretty similar spectrum here. So we go back to ADF jobs here, and we select the ADF job. We get the infrared spectrum. And sorry, I've got too many windows open now. So let's see if I can get a nice view of those on top of each other. Right, so you can look at the frequencies, and probably a few of them are shifted quite a bit, but as a first pass, DFTB is a very fast way of getting infrared spectra. And let's go on to UV-Vis spectra, so we can do the same type of comparison between ADF and DFTB calculations. All right, let me close these spectra window here. And let me see if there's anything else I wanted to say about this. Yeah, so obviously it can sometimes be useful to compare to the experiments. So if we go to NIST website. And so there's a specific link to propanel there. You will find the infrared spectrum and the UV vis, which we'll calculate in the next demonstration session. So if we click on the infrared spectrum, now I've already closed mine, but you can see that at least these major peaks and some of these fingerprints are reasonably well reproduced by using DFT or DFTB calculations. Good. Okay, let me quickly see if there's any questions that need answering. Thomas? Okay, all right. So if you have any questions, just shoot them at Thomas. All right, so let's move on to optical spectra. And let me grab one of the input windows here. So let's start with DFTB. We've already optimized our molecule here. And now we want to calculate the UV vis spectrum. So we don't need to re-optimize the molecule. We want to switch from geometry optimization to single point. Again, if I go a little bit too quickly, also on these slides, there should be direct links to the input files, right? So I will run now a GFN-XDB UV vis calculation. So if you open this particular hyperlink, well, probably you want to download that. You can directly open that with ADF GUI and you get all the input settings that I hope to be demoing soon. So we switch to a single point. I don't need the frequencies, so I untick this box here. And now I want to go to UV vis. If you don't know where to find UV vis, one option could be to use this search function here. And indeed, if I start typing UV, it will suggest here an input panel, excitations, UV vis. Good. So in this case, I'm particularly interested in allowed excitation. So since this has a singlet ground state, I just want to calculate the singlet excitations. And since it's such a cheap method, let's take 50 excitations. So there are two types of thresholds you can use within the time-dependent density functional-based tight binding formalism, which is a linear response theory, which is used to calculate the UV vis spectrum, either through the number of excitations or through a threshold of the excitation energy. And if you can't calculate quickly in Hartree, you can change these units by switching. So you left click on Hartree and you can change them to electron volts, or in this case, not nanometers, but when we visualize the spectrum, we can change them into nanometers. All of these are the settings. Technical settings we'll just keep as such. If you're interested in the single orbital transitions, you can calculate those as well. In this case, we're just interested in the spectrum. So I would want to save this as a different file. So we call this UV vis spectrum, propanol, DFTB, GFN, XDB. All right, save this. And we run the calculation. Again, that shouldn't take too much time. And once the calculation is finished, we can use the same spectra. So if there's infrared spectrum, it will visualize the infrared spectrum. If there's UV vis spectrum, it will visualize the UV vis spectrum. So we click SCM spectra. And again, there's a way you can use the Gaussian or Lagrangian broadening to make it a little bit more to your liking. So let's use a little bit smaller width here. So 5 point something like that. And so here, probably because I've visualized UV spectra before. This is in nanometers, but by default, if you haven't used this module, I think this would be in Hartree in atomic units. So if that's the case, you can just double click on this axis. So double click on the legend there, and there that will take you to graph options. You can switch the units to nanometers, which is the usual representation for UV-Vis, or if you prefer, you can switch to electron volts. Right. So in a lot of these graphing windows, you can change the behavior of the axis by left clicking on the legend there. Sorry about that. In this case, remember when we visualized the infrared spectrum, when we clicked on one of these little red lines here that corresponded to a normal mode, in this case, one of these red lines corresponds to an excitation. And so I seem to have broken here something. Let me quickly close this and reopen it. So I'll go back to Spectra. So for those of you who are running on Windows, I think there is some bug that if you click here on one of these top menus whilst you're in hessian Spectra, something is broken. So maybe now is a good time, because that happens when you develop software. Sometimes there are bugs. So maybe it's a good time to show you that on the main download page. This will take you to the releases which we currently use, but there are also, if you scroll down below, bug fixed binaries. And so for Windows, for instance, you could choose to download this one. So if you input your details there, you can download that version, which shouldn't have that issue I have with ADF Spectra. In the changelog, there will be a description. So there you go, indeed, ADF Spectra fix issue with using the menus on Windows. So this has already been fixed, but it hasn't been propagated yet to a new sub-release. So for some of these bugs, you want to use a bug fix, which helps you to deal with a little bit more up-to-date version. Okay, so let me switch back to UV-Vis spectrum with a little bit narrower lines. And let's see now if I select one of these. Yeah, so if I select one of these excitations here, it will take me to the particular type of excitation, and it will calculate or will display the contributions of the single orbital excitation. So for those of you who've listened to Eva John's talk, in the context of DFT, they can be meaningful in terms of their cone charm orbitals. And once we do the ADF calculation, we will visualize those transition orbitals, the orbitals involved in the transition as well. I think if I click on this, this will do nothing because, oh, it does actually. Do we get orbitals? We get orbitals in XTB. So if you click on one particular single orbital transition in XTB, indeed we do have the orbitals. In the DFTB, we don't have the orbitals. If you use the dftb.org parameters, we do if you use quasi-nano. So if you have the orbitals, you can visualize them. And so in this case, the main contribution to this peak here is from the occupied orbital 10A, which is visualized here, to the unoccupied orbital 12A. So it's a pi to pi star excitation. Good. Since I need another quick coffee break, let's set up ADF calculation and then let it run and come back in 5 minutes or so. So let me switch here from DFTB to ADF. So I go back to our molecular DFT code. It's fine if we just use the DFTB geometry, but maybe for good measure, we want to import the ADF optimized geometry. And let me demonstrate how that's done. So I shift left click to delete this, or Control A. And now I want to import coordinates, and that's done under File, Import Coordinates. And now I will select my infrared spectrum propanel because that has an optimized geometry at the PBED4 level. And if I open that, it will give me the optimized geometry at that particular level of DFT. Now for infrared frequencies, it's very important that we use the same level of geometry optimization, same level theory for geometry optimization as we use for the frequency calculations, because otherwise we're calculating gradients and second derivatives on a non-stationary point. For spectroscopic properties, it's less crucial, and sometimes actually you want to optimize your geometry at one level of theory and you want to calculate the spectroscopic properties at another. And for those of you again who've seen Eva-Jan's talk yesterday, besides having orbitals which have the correct asymptotic behavior for UV-Vis spectra, it's also useful to have exchange correlation potentials which have the correct asymptotic behavior. And in the context of UV-Vis spectra, that potential is SAOP, and that's a model potential. There's no energy expression, but it can be used for calculating spectroscopic properties. So let's change here from LDA to, where is it? Model SAOP, statistical average of orbital potentials. We keep scalar relativity, and double zeta with polarization is okay in this case. Sometimes you want to go to triple zeta to give a little bit more accurate results. And this model potential is only available if we don't use any frozen core approximation. Right, so using this setup, we want to calculate the UV-Vis spectrum. Now we know where to find it. It's under properties, but again, since we're in ADF, it looks a little bit different, but there we go. Properties, excitations, UV-Vis, type of excitations. Now ADF is a little bit smarter, so it can also make use of symmetry. So we use allowed only, so we'll only calculate UV-Vis excitations which are allowed in the symmetry groups. So for CS, that doesn't make any difference, but if you have a higher or a different type of symmetry, that allows you to reduce your calculation time by not including excitations which are symmetry forbidden. The default method here is a Davidson, but we also have a number of faster calculations available. So for instance, this delta epsilon, which is delta cone-Charm approach, which if the cone-Charm orbitals are represented in the correct potentials, are a pretty good approximation to linear response to DFT in the context of single orbital transitions. For small systems, you can use exact, but for most intents and purposes, Davidson is the one you would want to use, or you want to use for large systems, maybe one of these faster approximations. So there's Grimm's simplified Tam-Dunkov approximation and simplified TDDFT approximation, as well as a method which has been developed by Robert Ruger, a developer here in Amsterdam, which is also a fast approximation using DFT orbitals, but then the tight binding approximation for the linear response part. And so that can be a really fast method, and usually all the valence excitations can be really well represented by using that formalism. So if you're interested in UV-Vis, that's something definitely worthwhile to check out. maybe as a first part if you want to screen a lot of different molecules on certain type of UV-Vis properties. Good. Okay, so if you want to get a little bit more, let's say, insight into the excitations and the type of excitations, one can choose to calculate charge transfer descriptors and also do a more detailed analysis in terms of the SFOs. SFOs are symmetrized fragment orbitals, so you get more insight into the excitations themselves. All right, let me save this as UV-Vis spectrum propanol and then call it ADF SALP. Save this and run it. That shouldn't take too long either, but let's have a 10-minute break. Is that okay?
Yeah, that's absolutely fine.
Yeah.
If people do want to perhaps put some questions in the meantime,
Absolutely.
and
yeah.
we'll resume here again in 10 minutes. I think Thomas is also able to unmute himself now. So if you want to answer any of the questions as well by audio while you're having a break, then that's also good. So we'll see you in 10 minutes.
All right. Yeah. So just shoot any questions. I will go grab a quick coffee.
Yeah, if everybody can hear me, I'm happy to entertain questions.
Yeah, we can hear you fine.
So far, I have managed to catch up. At least doesn't appear to be anything open yet. So yeah, the main questions were about indeed licensing. And so the scheme is a little bit more complicated, and it depends on a lot of different factors. So the best thing is if you either contact sales@scm.com, or yeah, if you try filling out the online form for price quotes on our website, as well as yeah, talking to the persons at SCM in charge directly. Yes, that should. So the question about using a salvation model and then calculate an IR or UV-Vis spectra, that should definitely be possible. I don't have access to the screen right now, but yeah, you can indeed select a salvation model and run the calculation. That should be compatible with these features indeed. So there was a lot of question before about specific topics, let's say MBO analysis or bonding analysis in general. So for the sessions today, we pre-prepared some material which you can also download. I wrote down the link before. And yeah, so if should there be some time left in the afternoon, we will try to at least briefly talk about some of these things. I cannot promise that we can cover them in full detail, of course. That would be probably not possible time-wise. Yes, you can. So I assume the question about excitonic spectra of 2D materials, yes, that is possible. The calculation of excitations for periodic system is inherently way more expensive than for molecular system, but there is a tutorial on our website. So there's a specialized implementation in band to do these things. And if I remember correctly, there is also a tutorial. Let me just quickly paste the link here. So this should, yeah, basically exactly answer your question. It's actually on the molybdenum disulfide system as well. Yes, so we have phonon spectroscopy as well. That should be possible. Let me quickly start check if I can find some material on that. I'm not sure if there is a tutorial, but I'm pretty sure you can obtain phonon spectra.
You're doing band this afternoon, aren't you?
Yes, but I will focus more on electronic structure, so band structure. Of course, there are many other features which I'm not able to show directly, so or because of time. But yeah, I will demonstrate band from the graphical user interface. So yeah, here's how you calculate the phonons and IR spectra for periodic structures. So yeah, in the afternoon, I will indeed demonstrate one example on bands on 2D periodic structures as well, and yeah, and then move on to polymers, which are handled with the reactive force field. So the question about so to optimize states, I assume structures of ionic liquids. Yeah, I think you can. So if the question is about whether you can optimize the geometry, you can definitely do that. So with regard to the system, this should be universal. However, I'm not an expert on ionic liquids. What I could imagine is that yeah, you have to make sure that your ions stay ions, so you have to use the appropriate methods, so the appropriate functional or general chemical description, but in principle, yeah, there's nothing speaking against treating such systems. As far as I'm aware, our software has been applied for such cases as well. So let me go through this one by one. So the access for the program, I think the license will be on for a little bit longer, but I don't know the details. Usually they are. So you may have a couple of days to deal with that further. If that is not enough, you can also apply for a trial license on our website. So you basically have to fill out this form if that is not enough, and then you can yeah, use that for a month or so typically to evaluate the software in further detail and see if
the newsletter gives information saying that the workshop license is valid until the 29th of February.
Yeah, that seems that's the usual thing. Yeah. Mm-hmm.
And then to contact adftrials@scm.com for, as you say, your negotiating extended license.
Indeed. So coming to the next question, is it possible to optimize the geometry of a molecule having a molecular weight greater than 10 kilodalton? So the answer is, yeah, this is a pretty big system. So usually that's way beyond what you do with normal DFT calculations. You can definitely, I mean, it more depends on the number of atoms rather than on the atomic or molecular weight. So usually one can deal with, say, about tens of thousands of atoms if one uses a force field like ReXFF. For non-reactive force fields, that might be even higher. Yeah, I don't know what the detail is. So the what the details are in Material Studio, it really depends on what you are using. I know that was a different question. I'm sorry. No. So yeah, the atomic weight is not really the question or the quantity which is relevant, but rather the number of atoms. And indeed, so small molecules can be treated with force fields.
All right. Well, I've got some coffee, so I'm good to continue. Yeah. So this question on 10 kilodalton molecules. Yeah. So that's typically something you'd want to optimize with a force field. And for those of you who are around, question on machine learning, there will be some machine learning potentials coming up in the next release. So for instance, the ANI machine learning potential. So if you have a system that has carbon, hydrogen, nitrogen, oxygen, you would be able to use that on those type of systems. And so more and more will be happening. I mentioned that we have this centralized driver, which can do geometry optimization or other advanced potential energy surface tasks. So if you have a fast and good potential, you can plug into that. Be it a force field. So we're not really specialized on biological systems, but you can plug in OPLS, for instance. We do ship Amber. You can use that to optimize your system as well. So hopefully that answers that question. So let's see if this calculation has finished. I think it has. And then quickly move on a little bit because I think I'm going slower than I'd hoped. So if we visualize the UV spectrum calculated by ADF, again, maybe we want to change the width a little bit. So in this case, by default, we've only calculated the lowest 10 excitations. And if we're interested in visualizing the single orbital transitions, I think we looked at this excitation earlier on, right? So at around 200 angstrom, 200 nanometers, we get, again, if we just look at the single orbital transitions, roughly 3 contributions. So we see that the DFTB and the DFT give pretty similar results in this case. The MO looks a little bit more complicated. If you lengthen this window a little bit, you can, let me see if I can extend this a little bit more. You can change the, for instance, threshold cutoff here, make it a little bit larger. So these are the single orbital transitions in terms of the molecular orbitals. You can also visualize the natural transition orbitals, which are essentially transformation into one that maximizes those excitations in terms of single orbital excitations. And for those of you interested in visualization, there are a large number of different things you can do. So you can make a mesh if you want a finer grid. That's possible by changing here fields grid to fine. It will recalculate that. You could play around a little bit with the isosurface value, and if you left click on this isosurface here, show details, you can change all the color settings and so on in case you wanted to play around with that. Good. All right, let's move on. Maybe quickly do an NMR calculation and then do a little bit more potential energy surface exploration. And All right, let me just close a few of these windows here. All right, so let's take this molecule. We can either use this model potential, this exchange correlation potential, which has the correct asymptotic behavior, or for NMR calculations. So this can be a really good approach, but if you can afford it, it's recommended that you use a hybrid. So in this case, we choose hybrid PB0, and sometimes you want to use a little bit higher percentage of Hartree-Fock exchange, and more on that later on. And usually you'd want to go with at least triple zeta with polarization quality. And we switch now. We don't want to calculate excitation, so I switch off type of excitations to none, and properties, I will go to NMR, calculate the nuclear shielding for all the hydrogen atoms, and I'd also want to calculate the spin-spin coupling for all the hydrogen atoms. And we save this as NMR for propanol. Again, those input files should be available directly from the link on the hands-on slides. All right, so it gives us a warning. There's nothing to worry about. It uses an old exchange correlation kernel that has to do with the response properties of the nucleus. We go run, and hopefully that should take long enough to give me some time to point you to another part of the website. On the support page, there is frequently asked questions. So the NMR implementation in ADF has been done mostly by Johan Ouchbach at Buffalo. And he has a really nice number of publications that make for good background reading. So if I switch FAQ to ADF, and I'll find here what settings are recommended for NMR calculations. And you will find links to a couple of examples here. And indeed, it mentioned we should use all electron basis set using at least triple zeta with polarization quality or better than that. And TZ2P, so you have two polarization functions, is usually a very good choice. Sometimes you want to go a little bit higher quality than that, but it becomes really expensive in terms of basis sets if you go to quadruple zeta. There's a specific basis set, JCPL, so J coupling, which has been specifically optimized for spin-spin coupling calculations, and indeed it recommends PB0 is often a good choice. If you can't afford that, then Johan recommends to use PBE or this model potential SALB. So yeah, I'd recommend, if you're interested in NMR calculations, to have a look at Johan's work, and those are really good background reading on running those ADF calculations on NMR spectra. Okay, so my job is finished. I hope the same goes for you as well. And now we can use again SEM spectra to visualize the NMR spectrum. And by default, you just get the shieldings, right? And since we calculated the coupling, we can also include the coupling. And I think in my examples, I suggested to compare coupling. Okay, so this ADF spectra on Windows is not the best. So let me reopen it again. So as I mentioned, there were a few bugs which were ironed out. If we change this to 400 and switch on coupling, it will calculate the spin-spin coupling. And if you select any one of these atoms, it will tell you also to which other atoms it is coupled. And sorry about that. So yeah, let me do that once more. So sorry for those of you who are working along on Windows, they're feeling the same issues with this ADF spectra as I am. So if you select again one of these atoms here, the coupling here to the other hydrogen atoms is given once you select them, and it gives you the splitting pattern. One more thing. So by default, obviously, also when you run the calculations as you do with the experiments, you need an internal standard. And here the standard is TMS for both 1H and 13C. And there's a default value that the graphical user interface uses. And that is, if you hover your mouse on it, is given for a calculation on tetramethylsilane using a TZ2P basis with the blip exchange correlation potential. So in this case, we use different DFT settings. So you'd want to calculate TMS first using those same settings and use that as an internal standard for your chemical shifts. It's probably not going to make a huge difference here, but it's definitely something you should do when you run your production calculations. All right, so let's go on and explore a little bit more potential energy surface properties. First thing that we want to do is see how many conformers we have. Well, we already seen 2, and I think that's pretty exhaustive for this case. So it's going to be a little bit silly demonstration, but let's do it nonetheless. We switch from ADF to conformers. And we get to an input panel where we can calculate a number of conformers using RDKit. And RDKit is randomly going to perturb this system. It's going to try a local optimization using its own version of a universal force field. And then it's trying to go into see if it knows already a particular conformer in terms of the ones it has found before, and for that it uses a filter, and you can change the tightness of that filter, and then at the end there's going to be a refiltering of all the conformers, and so you can set the final root mean square filter criterion for that as well. Usually the defaults are pretty good. So if you go to a larger molecule, it will take a little bit longer, but in this case, this will be pretty quick. So we save this as propanol conf and run it. And it's generating conformers, it's done, and we see nothing, but luckily we have a hint here. So we use ADF movie, SCM movie, we can see our conformers. So in this case, the movie, which we use also to look at geometry optimization, gives you, well, not really a trajectory, but it gives you a representation of all the conformers in your system. So in this case, we have S-cis and S-trans. Right, okay, so probably if we have these 2 conformers, there's going to be a transition state that connects those 2, and let's see if we can find that, and hopefully after that we can get to a little bit more serious transition state before the end of this session. And one of the aspects that we are going to use in this example is a potential energy surface scan, and we'll use DFTB for that. So I switch from conformers to DFTB. Probably for good measure, usually you'd want to use a new input file, because sometimes some of the settings you've chosen in the graphical user interface are somewhere saved and they're not particularly amenable to the kind of calculation that you want to run. So I'd actually recommend in a lot of these cases to go to File, New, and make a new input. Right, so I'm just going to live on the edge in this case, and I am going to use this particular molecule here, and I change my task from single point to potential energy surface scan. And now I have this little arrow here that will take me to this input panel. So geometry constraints and potential energy surface scan. So this serves both purposes. So potential energy surface scan is where we constrain 1, 2, 3, or any number of coordinates or a combination of coordinates, and then optimize all the other coordinates at the same time whilst keeping that constraint. Once that point has converged, we move on to the next one. Okay, so in this case, I want to scan around this dihedral here. So I select each one of those in order. So remember that's Shift, hold down Shift while I click each one of these atoms. So let me do that one more time. Shift, click 1, click 2, click 3, click 4. I've got my dihedral here, and I click on plus, and it will create here for you a scan coordinate. So this SC stands for scan coordinate, and in this case we just want to scan the dihedral. But sometimes you want to have a composite scan of coordinates, and hopefully we'll get to that once we look at the Ziegler-Natta catalyst. I want to scan this from 180 degrees to 0 degrees, and I want to do that in steps of 10 degrees. So I need 19 points, including the start and the end points. All right, so let's see if we want to use this model. Yeah, XTB, that's fine. We save it as scan acrolein, and we run this job. Now, whilst this job is running, we can follow the progression here. So if I go to SCM movie, and I have to drag that again into the viewport here. So you can see it is optimizing within the next set of constraints. Then once, so in this case, we have an angle of 10, and then it moves on to the next point, next point, next point, next point, and so on. And this looks a little bit messy because it doesn't realize that some of these, now that all these points are optimized. So let me see if we can change this by changing the view. It isn't. So normally for these kind of things, you want to go to accepted geometries only. So we close the window. And once the job is finished, we go to SCM movie again. And now the default view would be the optimized geometries only. So if you want to see all the optimization points in between, we can untick this, but actually this is a rather nicer representation of what's going on here. So we see that we have an increase to around, well, around 90 degrees. So that's roughly where our transition state should be. And then we go downhill. So this is probably the geometry that we want to use if we want to start finding a transition state. So I will save this geometry, save, and I'll save it on my desktop and TS start. And I go back to my input window here. And actually now I will just make a new input. So SCM new input. And I will import those coordinates. So file, import coordinates, go to my desktop. This is my XYZ file. And now I switch my task. Sorry, I go to DFTB. We can run ADF as well. I'll switch my task to transition state. And so for transition state, usually you'd need two things. You need to be close to your transition state geometry, and you need a good guess of the curvature. So ideally you want to use an input hessian, or at least you want to use the normal mode vector for your lowest mode, which corresponds to your transition. So again, we use this arrow here to go to the details, and there's an option here to choose an initial hessian. So you can calculate it automatically, which is usually a good choice, but you can also calculate it. And since we're using DFTB, this is going to be rather cheap. So let's just calculate the hessian here. And to verify it's a transition state, after it's run the optimization, we also want to calculate the frequencies. So we were using XTB when we're running the scan, so we'll also use that for our transition state here, and we save this as transition state acrolin DFTB. And let's run this. So now if we have a look at the log file, it will calculate the hessian. And since we're rather close to the transition state, and we had a good idea of the curvature, we had a good hessian, it is really, really quick. And so this is our transition state here. So let's say a little bit higher than 90 degrees, so 93.7. And let's have a look at the infrared spectrum and visualize this imaginary mode. So this negative frequency here. And indeed, that would correspond to transitioning from S-cis to S-trans. And if you're interested in that process in polymers, Thomas in the afternoon will show when you tear apart a linear polymer chain, which has these type of bonds, you will find similar transitions during that process. If you want to be absolutely sure that this transition state connects your reactant with your transition state, then you can run an ISC calculation, or you could also run a natural elastic band and use that as a starting point for your transition state search. So hopefully we have time to get to that point when we discuss the Ziegler-Natta catalyst. All right, so now, because I think this can be very useful for actual pragmatic cases, let's see if we can take this geometry that we have, which is a transition state at the DFTB level, and pass it on to ADF to do a transition state calculation at the DFT level, and also make use of the hessian that we calculated with DFTB. So I will switch from DFTB to ADF, and I will set as a task here again transition state. And now in the transition state detail window, transition state search detail window. It looks a little bit different as it did for DFTB. We have to click on one more time to get the initial hessian. And the initial hessian now, we see this little folder icon here. We can read it in from our previous calculation. So we search for previous calculation, TS DFTB, and we select dftb.rkf, from which we can read in the hessian. And let's take a different functional. Let's take a meta GGA. Let's take the Minnesota 15 local functional. Again, choose scalar and choose DZP. With these meta GGAs, you have to be a little bit careful that they can become a little bit numerically sensitive. So usually it's recommended that you use a little bit higher numerical accuracy, specifically the integration grid. And we use all electron calculation. All right, let's see if this works. We save it as TS acrolein ADF. And there should be a input file which is pretty similar to what I just did, available through a link on the slides for the hands-on of the morning session. Now, this being a ADF calculation, also with a meta GGA, it is bound to be a little bit more computationally expensive than the DFTB calculation. So you see it takes a couple of seconds for each of the SCF cycles to calculate the energy and the gradients. And it's probably taking a few steps to converge to the transition state. If we want to visualize that, we can go to SCM movie. And we see here the energy. Obviously, since we're going to transition state, the energy doesn't need to come down because we're optimizing to a first order saddle point, but the gradient, which are depicted here in green, so the root mean square and the maximum gradient, those need to come down. And in this case, indeed, it takes 3 steps for the transition state to converge. Okay, so let me go to the slides I have here. Yeah, so one more thing I wanted to do just to see what is also possible with Cosmo RS very quickly without having to install the database. So I've got too many windows open. All right, so from any of the graphical user interface windows, if we select SCM Cosmo RS, and for those of you who do this for the first time, probably will prompt you to download a database, which you don't need to do, right? So it will look like this. So in this case, we don't need it. If you want to get into that, there's a database of around 1900 compounds for which we've calculated the surface charges using a set protocol for which Cosmo RS and Cosmo SAC have been parameterized. Right. There's also, besides using these surface charges from an ADF or a MOPAC calculation, there's a very quick way you can calculate these surface charges based on a group contribution method, and that takes small strings. So if you have an XYZ of a file that can be converted to a SMALS setup, you can also import that XYZ file. So remember, we just saved a XYZ file, TS start. Just open that, add it, and call that, I don't know, acrolein cos. And that is just based on the connectivity. So it will automatically generate the small string. And for those of you who present at the beginning of the session, that was indeed the smile string that we imported into the graphical user interface. Now, once we have that smile string, we can calculate a lot of different properties, or we can calculate them instantaneously, and the estimation can be okay. So let's just do that. We go to properties, pure compound properties. We take this molecule here and we run it. And here you'll find a number of estimated properties based on this QSPR prediction. For example, here we have a boiling point, and I think I have a link here to Wikipedia, which again we visited earlier today. So Wikipedia, we can probably find a boiling point as well. So it's 326 Kelvin, and the predictions were around 60K off. Sorry, 20K off, so 345. So it can be a quick way to estimate properties of molecules which are reasonably well represented within this QSPR model. So if you're interested in that, let us know. If you want to do a little bit more accurate predictions, then you can do the full-blown COSMOS calculation, and then you can also calculate properties like solubilities or partition coefficients. You can use it to calculate more accurate solvation energies. So, for instance, reaction energies in solution, pKa values can be calculated more accurately, and so COSMOS is not the same as COSMO. So COSMO is a polarizable continuum model, but it sort of extends beyond COSMO, and the RS part for COSMOS stands for realistic solvents. The SAC model, which is also available, stands for segmented activity coefficients. So essentially, you can switch between those. We also have a UNIFAC implementation, and the activity-based coefficient methods that use these surface charges from a calculation that uses COSMO. Good. Okay, this is just a very quick demo on how that works. I'm not going to save those. And let's see, I think, well, we have around 30 minutes. Maybe we can make some headway in calculating a little bit more interesting transition state, but let's just see if there's any urgent questions at the moment. Thomas?
Yeah, that was a big question about comparing some modeling suite to
Okay, well, we can discuss this. There's going to be a 1-hour discussion session after this as well, right? So we can discuss that later on. Anything else? I see, can you calculate properties of periodic structures? Yes, you can, and this will be done in the afternoon session. I see a fusion point for some solvent. Is there something similar for crystals? Yes, you can calculate, or you can estimate the heat of fusion and the melting temperature, but it's to a very limited set of types of material, so it wouldn't work for inorganic systems, for instance. Good. Okay. Let me just move on to calculating tricia states for tricia metal complexes, and let's start with a completely new input. So we go to SCM new input. Why does that not give me a new input? It's probably in the other window. Okay. Let me close a few of these. Sorry about that. Yeah, I've got two screens, and the one that you see is not the one where I get my new input windows. Okay, so what we'll be looking at is a transition state for polymerization reaction using zirconocene. And let's start building such a molecule. So this little hexagon here, benzene-like structure, has a structure library of a number of different, let's say, templates. And you can use those as a starting point to start building structures if it's not easy to do in any other way. So for instance, we've seen different ways you can import molecules, but sometimes you want to build them from scratch, or sometimes you want to use a certain motif in different types of molecules, and you can use your own library as well, so you can save a molecule as a type of building fragment. All right, so in this case, we want to go to metal complexes and want to go to sandwich complexes, and I want to use dipentacene, cyclopentadienyl complexes, and the default structure is ferrocene. And so ferrocene, so this is one of the two isomers of them, has iron in the middle. In this case, I want to swap out iron for zirconium. So I can either select this and then edit, where is it, atoms, change atom type, and then I get this window here where I can choose zirconium. Or you could have right-clicked on it and then also there find the option change atom type. So if it's selected, right-click, change atom type. And that feature is also useful if you want to, for instance, modify this particular ring here. So if I want to change this to a methyl group, I can right-click on that and replace by structure. Go to alkyl chains and change that into CH3. Okay, let me undo that by Control Z. So I've got my cyclopentadienyl again. And by default, there are some centroids in here, which sometimes work nicely, sometimes not so much, but you can use them as geometry placeholders, so to say. So in this case, you can open up the angle a little bit here, and we can also change the distance between the metal and the ring itself. And so the way this distance tool, so we've used this slider before, is that by default it will move away the last one that you selected. So in this case, I selected the centroid as atom 2, and if I change the distance, that atom will be replaced. Now the resting state for the Ziegler-Natta catalyst here looks something like this. So there's a methyl group, and the methyl group we can add. Where's my input window? By selecting the central zirconium, press on C for building a carbon atom, and then just sticking a carbon atom here. And that carbon atom I want to saturate with hydrogen atom, so press Ctrl E. And now I've got my my catalyst here. I will optimize this with DFTB, and since the DFTB 0 and self-consistent charges DFTB or DFTB 2 and DFTB 3 don't have any parameterization for zirconium, we will use GFN-XTB, which has parameters for most of the elements in the periodic table. This is a cation, so I want to change the total charge to 1. And typically these reactions take place in solution, and toluene is one of the solvents that is used quite a lot. So we go to model, solvation, And so in GFN-XDB, actually, we don't use a polarizable continuum, but we use a generalized Born solvation model, again, from the group of Stefan Grimmer. And we choose Toywin here, so there's a number of presets. So the solvation model is called GBSA. It's an implicit solvation model, and especially for ionic systems, that can make a huge difference on the geometries and the energies. So select Toywin, go back to the main input panel. Let's see if everything is okay, and save this as CP2 zirconium methyl, and let us run this job. See if that gives us a sensible structure. Again, if that went a little bit too quickly, I made an input file available. So if you right click on the slides on this .adf, that should allow you to download this particular input file. All right, so once the structure is optimized here, this is going to be, let's say, the starting point of our catalytic cycle. I'm going to remove the centroids here because sometimes that can mess up a little bit the geometry optimizations, because the ordering of the nuclei can be a little bit changed because they're actual atoms in the GUI, but they're not actual atoms in the optimization itself. Right, now I want to start my polymerization reaction. So I start with ethylene and search for ethylene here, or ethene. Let's see if we can find that. There we go, ethene. And whilst the molecule is still selected, you can use your right mouse button, select one of the atoms and drag it along. So right click that molecule, whilst you hold it, you can drag it around, and select one of those atoms and left click, and you can rotate it and see if we can find a sensible place for it. So it's a little bit fidgety. Select the molecule again, Control M, drag it around, rotate it with the left and the right mouse button. It's a little bit, takes a little bit practice. Let's see if we can get it somewhere where we want it to be. So what will happen in the catalytic cycle is this alkene is going to bind, then it's going to insert into this zirconium carbon bond, then it's going to open up, and then there's room for the next monomer to attach itself to this the zirconium center, and the cycle can repeat itself. All right, so let's see. We have to try. Give this a different name. If this gives us a sensible starting point for our reactant state. All right, so we run this. And let's see if that gets us anywhere sensible. If it doesn't, then finally, when we get to the point where we want to do a potential energy surface scan, which is going to be the next step, you can download the input file I have here, so you can follow along with that part of the demonstration. All right, so my job is finished, and that to me looks kind of sensible. So let me just give you a minute to see how your geometry is converging, and if it didn't, maybe you want to go to this slide, so slide 17, right click on this particular link and download the input file. Good. Okay, so regarding finding transition states, what we did for the acronym was quite simple. We just changed the dihedral, find the highest point. In this case, is a little bit more complicated reaction. So essentially, this carbon is going to bond to this carbon atom and open up the zircon carbon bond here. And this atom is also going to be a little bit more strongly bound to that zirconium at the same time. So there are two things happening at the same time. Let's see if we can set up a potential energy surface scan to reflect that. So we change here from geometry optimization to PES scan as we did before. Click on the arrow to go to the details, and I want to set up a potential energy surface scan where I scan this distance here to 2.4, and I also at the same time want to scan this distance to something close to a single bond. And by default, since I've now selected a different coordinate, it will have assigned a different scanning coordinate, but I actually want to have a composite scan where I increment, or sorry, decrease both of these distances at the same time. So it's going to be a composite coordinate that we will scan in this particular example here. Right, so I think in my example, I actually had a slightly different setup, but so let me, yeah, so it's the distances are pretty similar. And let's see if we can scan this in 10 steps. Since I'm not really interested in the entire reaction pathway, but just the highest point, I don't really want to optimize all of the other coordinates. So to speed up the potential energy surface scan, what you can do, and I would recommend you would do, is to slacken a little bit the convergence details. So I will change, so this is available on the details geometry optimization, or through the arrow, just click through, change the gradient convergence to be sloppier by a factor of 5, and each one of these criteria. Yeah, because I'm not doing a geometry or a transition state optimization, we're just getting a rough idea of the potential energy surface. I don't want it fully converged for each one of these scans along the potential energy surface. All right, let's save this. So CP2 zirconium insertion scan. Let's see if that gives us what we wanted to give. So finding transition states is always a little bit more of an art than a science, but if you get more and more experience with this, then you can think about, I have some tips and tricks on the last slide as well on what would be a good way to get close to your transition state and also get a good guess on the curvature of the potential energy surface. And that will help you find more transition states rather than converging back to your reactant or forward to your product state. At the same time, we are working on finding more and more transition states automatically. So if you're interested in those type of calculations, stay tuned because there are a few projects that we're working on in the context of EU collaborations where we should have more robust tools for exploring chemical reaction networks. So my calculation is finished. I'll give you a couple of maybe a minute or so to see how your calculation is progressing. And so now I've imported the last structure or the last optimized structure in the graphical user interface. I've updated geometry, but it still thinks it has the same connectivity as it had for the point that I started with. So if I want to have, let's say, a little bit nicer representation, what you can do is go to bonds, guess bonds, and deselect my system here, bonds, guess bonds, and here we get a single bond, a single bond, and a single bond. You can nicely see actually that this hydrogen atom is agnostically bound to the zirconium, and it's a little bit extended beyond what the GUI would still find acceptable as a carbon-hydrogen distance. I don't know the exact thresholds, but yeah, it's unusually long for a carbon-hydrogen bond, and that's typical bond length for an agnostic bond to a transition metal. Okay, so whilst I was chatting about that, maybe your local calculation finished. So if we go to SCM movie, as we did before, again, that ends up on the wrong screen. We'll find here, these are the optimized points along that scan coordinate. Yeah. So let's take the highest point as a starting point for our transition state calculation. That should be a pretty good guess. And we go File, Update Geometry in Input. There we go. We want to change the convergence criteria back to the defaults. Because we want to optimize the transition state. We want to make sure that we converge to the first order settle point. In the main input panel, we switch from PES-scan. Let me first do this. So this is also why I mentioned probably you want to use a new input for good measure. We want to make sure there are no constraints here. So we want to remove all of these entries here on the geometry constraints and PES-scan. Sorry about that. Go back to the main input panel, change from PES-scan to transition state. We do keep the same XTB with toluene as a solvent setting. And in the transition state detail panel, we will choose to calculate the hessian because that gives us the best representation or the best curvature, and that will give the optimizer the best chance to actually find the transition state in this case. Right, save this. Save as CP2 zirconium insertion transition state. And let's run this. And as I mentioned, transition states are by no means always a guarantee, but we'll try to do our best to find these transition states. And it's first calculating the hessian. For XTB, there are no analytical second derivatives, so it takes a little bit longer the larger the system is because it's taking numerical second derivatives. So it displaces each one of these atoms, calculates then the derivative of those gradients, and that then calculates the hessian. And so in this case actually was the longest part of the calculation. give you a little bit more time to see if your calculation finishes as well. Okay. Do want to read in the new coordinates, and okay, maybe this actually is a transition state. So I want to re-guess the bonds here. And so yeah, don't attach too much value to these graphical user interface bonds. But yeah, it's somewhat, I guess it's somewhat of what I would expect. So this carbon is still bound to the zirconium. The hydrogen is, but it's already lengthening, and we start forming a bond here. Now let's go to the movie, which will show us the optimization, and there we can see what's happening in terms of the transition state optimization here. Again, we want to verify that this is a transition state. So what I should have done is actually select frequencies here, but now we have the optimized geometry. We can also do a single point calculation and only calculate the frequencies. So save as. Something similar, but then with a different name that we want to calculate the frequencies. So for first order setup point, the transition state, we should have one and only one imaginary frequency. And as we experienced previously, this is going to be the most expensive part of the calculation, calculating this numerical hessian. And so if you get to larger and larger systems, there's also an option, if you just want to ensure that you have a transition state, to use PES point characterization, so potential energy surface point characterization, to ensure that you indeed have only one imaginary frequency, one negative eigenmode of the hessian. All right, this frequency calculation is finished. So I've selected that job, and if I go to SCM spectra, and we should have indeed only one imaginary frequency, and that indeed corresponds to the insertion reaction. So I'm pretty confident that this is indeed the transition state for insertion of ethylene into the growing polymer chain. So the polymer chain is pretty small at this stage, but if we get to larger and larger systems, we have similar types of transitions. So if you're not as certain as I am, then you can run a ISC calculation. There are tutorials available for that as well. But in the last 10 minutes, let me show a different way you can use to get a good guess on the reaction pathway, as well as getting a good starting point for transition state, and sometimes even calculate the transition state. And the method that we'll be using is called nudged elastic band. And for nudged elastic band, what we need is a reactant state, a product state, and if you have it, you can also include an intermediate state. So in this case, we've optimized our reactant. So let me go back to ADF jobs. Right, so this is our reactant here. And I'm sorry that all these windows keep opening on the wrong screen. This is our reactant here, and we did this little scan here, and we can use that. So we take the last geometry of that, we can use that as a starting point. So it asks you to read in the last coordinates. We can use that as a starting point for our product. So if we change, so remove any of these constraints here, and we change that to a geometry optimization, we can save that as CP2 zirconium insertion product, save, and let's run that. All right, so this is our product state here, and we want to use that as one endpoint and the reactant state as another endpoint of our notched elastic band. And in the example file I have here, actually we have a 3-point notched elastic band where we also use the end product. So you can find that here, or maybe we can do it as well. Let's just do it. I think we have 9 minutes, we should be able to do it. As long as I can find the correct input window. This is our product here. So there's a little bit more stable product, which I will delete this bond here. I will create a single bond here by selecting those two and pressing add bond, Control L. And we add a bond here as well. We'll re-optimize anyway. So there's a little bit more, make this a single bond, a little bit more stable product. So this is the gamma hydrogen bound here to the zirconium, but actually zirconium is very happy in 4 centered rings. And so if we rotate this particular dihedral to get this hydrogen atom to be in the neighborhood of that zirconium, so something like that, like a dihedral close to 0. If we use that as a starting point, we will optimize the actual end product of the insertion step and save that as CP2 zirconium insertion beta hydrogen. And again, do a geometry optimization. Now then we should have a reactant state, intermediate state, and an end product. And we will set up a notched elastic band between those 3 points. Let me see if that optimized. So there we go. So indeed now we have a 4-membered metallocycle, and so for those of you who've worked with zirconium and those early type transition metals, they tend to be a little bit happier in 4-centered rings than in larger rings, especially when you have these agostic type of bonds. Okay, here we go. We set up a notched elastic band. We change here the task to NEB and click on this arrow here to go to our setup options for NEB. Since now we have actually an intermediate and a product, I want to use a little bit larger number of images. So notched elastic band essentially is trying to optimize a reaction path from the endpoints to the transition state, and each one of these points along the way is connected through a little spring, and the whole band is allowed to relax itself along the reaction direction path. Let's take this as the initial system. So in the drop down, I will find mol1, which is, well, let's take this as a final system actually. Final system, mol1. And the initial system, I will choose my reactant state. So in the drop down, choose new molecule. And in molecule 2, I will import the coordinates for the first reactant that we calculated. So I go to File, Import Coordinates. have to scroll down to, what do we do? That was the one, but I want the result file. So I scroll to the folders, the directories, and I go to the CP2 zirconium methylene results, and choose ams.rkf, which contains my final optimized structure. All right, yeah, so that was the reactant state. And for the intermediate state, I again select new molecule. And for the new molecule, I'm going to use this intermediate molecule file, import coordinates, go back to ADF data. And there from the product.results, again, choose ams.rkf. And that was the 5-membered ring, so the gamma agnostic product. So let's toggle. This is our final system. This is our initial system, the ethylene at a distance. And this is our intermediate system. I am going to dial down the convergence criteria a little bit. Yeah, so something like that. So that is probably good enough for the NEB. Usually you don't want to use the NEB to converge all the way to the transition state. It can, but sometimes it can take a long time. Usually you'd want to use it as a first good guess to your starting structure for your transition state. All right, let's see if this works. We save this as CP2 zirconium. Let's call it NEB. Again, there should be ADF input files available for download from the website. And now it needs to optimize essentially 12 structures at the same time. It's going to optimize the gradients, which are perpendicular to the springs to which it is attached to the next image. So it's going to optimize all the coordinates except for those projected out in the direction of the notch elastic band itself. Usually visualizing this is not so useful until it has converged, but let's see if we can already see something happening in ADF movie, and hopefully it will finish in the last 3 minutes. So yeah, now you see actually each one of these points, you see the gradients and the energies. So each one of these little hills corresponds to your path, and hopefully the whole of the path would be converging to something that is your final reaction path. Okay, let's see. In my case, it has finished, so just in time. Now again, if you close ADF movie and reopen it after it has finished, it will by default only take the optimized points. You should get something like this. So if you scroll along that, you'll find not one, but 2 transition states. So this is the one here, which actually has been optimized by NEB. So that is our climbing image. But further along the line, we'll see that, okay, we have, this is somewhat close to the intermediate we calculated before, but through this rotation here along this dihedral, we find another transition state. So if we take this point and want to run a transition state calculation on that, that would be a good starting point. And then we finally move on to the end product here. And now we're in a resting state. We can attach another ethylene, another monomer, go through the insertion process and keep building our linear polymer. Okay, so I hope this has been useful. For those of you who are interested in tricia states, there's a final slide on some further considerations. But let's stop now and see if there's any further urgent questions. But I think Rebecca and Goedele, there's going to be a 1-hour discussion session anyway, right?
Yes, that's correct. So if anyone has any sort of urgent questions, we can do them now. But if I think you're probably quite exhausted after that. So the discussion session will start at 2 p.m. Central European time. So if you're around then and can join us, that would be great.
Yeah, all right. Sorry. Yeah. So the discussion is from 2 to 3, and then there's a coffee break, and then the afternoon session starts at 3:30, right?
Yeah, perfect.
All
yeah,
right,
there are questions appearing. So I don't know, do you want to take them now or later?
Sure.
Okay.
Sure. Yeah.
Because there was a question on how do IDF jobs parallel?
Yeah. So it sort of tries to be clever and does it automatically. So depending on the job type and the number of cores which are available, it tries to use all of them. So if it's a small job and it doesn't make sense to go parallel, it doesn't. But I think in this case, for instance, you will find if you go to a job file, here it uses just a my machine, so a single node for processors. If you want to change that behavior, there are a couple of things you can do. So you would have noticed in ADF jobs, there is this little box here that's an input option box, and for the default sequential queue, you could change that default behavior, and in this case, I set it to 1. That would use just 1 core. So just quickly demonstrate what it looks like in terms of the queue configuration. So this is your sequential queue, and essentially here it says NSCM, which is our environment variable that sets the number of cores you want to use, is $option. So that's an environment variable which you can change before you run the job in this little rectangular box here. Another option, so if you run the job from the command line, you can set NSCM explicitly here before you run the job. So NSCM is the number of cores you would want to run on. And finally, there's under SCM preferences, you can set your environment variables, and there you could also explicitly set NSCM. I'm just looking backwards. Thomas, did I forget anything on parallelization? Yeah, so does that answer your question, Labanya? Okay, good. And then I see a question on MBO. Is it practical to move to ADF, so to use localized molecular orbitals to visualize the nucleophilic sites from the LUMO and partial charges on the atoms? Yeah, so to that question, yes, you can use and visualize with ADF MBO properties and localized MOs, and actually there are a large number of different ways you can use conceptual DFT. I know there were sessions on conceptual DFT earlier on in this winter school, and we tried to support as many of them as we can. So yeah, you could do that.
Okay, thank you. Questions about video and slides are popping up. So we recorded this talk and it will be made available through the website, but it can take 1 or 2 days before we post
Yes.
the video.
So the videos are left to you. For the slides, they should be available. Let me copy and paste a link to the news item here. So if you, let me paste this in the chat box. So if you go to that news item, there should be links for downloading the slides. Also, for those of you who will be attending the afternoon session, which again is going to be done by Thomas and Ola. So I will take over Thomas' role in terms of answering questions. You can already download their slides and input files as well. So these links here, these are my slides for the introduction, the exercises, and there's a zip file with all the input files as well.
Okay, thank you very much. There is another question coming in.
Okay, so how do you execute MBO analysis in ADF? So yeah, there's a tutorial on that. And so with your evaluation version, MBO should be activated, so you could use that. Let me just go to Graphical User Interface getting started. And so if I search for MBO there, so there is a tutorial which I mentioned. There are a lot of, let's say, analysis options. And so this also discusses atoms and molecules, as well as a couple of other conceptual DFT aspects. And yeah, so there's a section there on using MBO analysis specifically for NMR. And again, this is work by Jochen Autsbach. So if you go to that tutorial, that should show you how to use the MBO within ADF. So you can visualize these localized molecular orbitals from the same graphical user interface that we visualize the MOs for the excitations for, but you need to tick the MBO analysis when you run the calculation.